Hello to all of you future mathematicians. Today I would like to talk about the animation that you can see behind me and a little bit about the mathematics behind it. As we shall see, basically everything here are a lot of triangles tiling some sort of plane. But before we can talk about this, we need to talk about general tessellations or general tilings of the plane. So what is a tiling or a tessellation of the plane? Well, in its most general definition, a tiling is basically covering the whole plane with shapes without leaving any holes or gaps behind. But this is a very general definition, and you can argue that this is a tiling. You take one big shape and cover the whole plane. But this is a very trivial tiling, and usually the most familiar tiling that we all know about is the square tiling. And there is a good chance that if you look at the floor right now, you will see this sort of tiling. Another well-familiar tiling is the following of the rectangular tiling that we can see in many walls. Here all of the rectangles are horizontal, but there is nothing stopping us from taking horizontal and vertical rectangles. And in general, we can take any sort of shape or size of a rectangle. And if you really want to go wild, we can take any sort of polygon or any sort of shape that we want. At this point, if you are really creative, you can add all sorts of patterns to your tiling to make them much more interesting. So we saw that there are a lot of tilings, and the question is, how do we study them? Well, in general, if you want to study a tiling, you look at two things. The first one is the shapes of the tilings, and the second one is the symmetries. For example, if you look at this tiling, then there are two shapes of tiles. One the horizontal rectangle, and the other the vertical rectangle. Or if you want, there is a single rectangle with two orientations. For symmetries, we can look, for example, on walking a little bit right and a little bit up, and you will see that if you move right and up, then you will see the same tiling again. Of course, there are many other symmetries for this tiling. If you choose the right amount and translate to the right or left, up or down, you will see again the same tiling. Okay, so now we know about general tilings. Let's go back to our original tiling. So now we need to know what is the shape of our tiles and what are the symmetries. So for the shape, we're going to take the triangle, and for the symmetries, we're going to take the reflections. So for example, start with a single triangle, and then take its reflection through one of its edges, and then another reflection, and another reflection, and another reflection, and try to use this process to cover the whole plane. If you do try it, you might find yourself in some sort of a problem. So what do I mean by that? Suppose that you take a reflection of a reflection of a reflection, and eventually you get to this triangle. But what happens if you take another route of reflections? So you take a reflection from another place, and again you get to the same point, but suddenly you get another triangle. So you have two overlapping triangles which are not the same. And this is a really messy image. So we don't want it. So one sort of condition that if two triangles intersect, that they must be the same. So let's see an example. So for example, start with the standard triangle, and then take the reflection from above and the reflection from below. And then you do it again, and again, and again, and again, and eventually you will get this sort of problem. So if I take another reflection from below, then I will have an intersection, but the two triangles are not the same. And this is not the nice tiling that we look for. So how do we fix it? What sort of condition that we need to ask so we will not have this problem? Okay, if we denote the angle by theta, then basically if you want to avoid this clash when you go around the vertex, then theta must divide 2 pi. Or in other words, there is some integer k, such that k times theta is 2 pi. But actually we can say something even stronger. This theta goes from red to green, but then we must go from the green to red with the same angle. And then again from red to green, green to red, red to green, green to red. So if we really look at it, then not theta divide 2 pi, actually 2 theta divide 2 pi. Or we can also say that theta must be of the form pi divided by some integer. Okay, so this is true for a single angle, but this must be true also for the other angles as well. So our triangle have the angles of theta divided by n, theta divided by l, and theta divided by m. Well, this is a triangle in the plane, so we know something about the sum of the angles, so the sum must be pi, and if we divide by pi, then 1 over L plus 1 over M plus 1 over N equals 1. Okay, so we got a very nice necessary condition if you want to tie the whole plane with triangles and use reflection to go from one triangle to the other, then we need this condition to hold. I will leave it as an exercise to show that this is not only a necessary condition, but it's actually a sufficient condition. If this condition holds, then the tiling will cover the whole plane, and every time that you will get to the same point with two triangles, they will be the same. So now that we have this simple condition, we can look for all the triplets that satisfy it. And there aren't many of them. The first one is 2, 4, 4. And notice that 2, 4, 4 means pi over 2, pi over 4, pi over 4. So 19 degrees and 45 degrees and 45 degrees. Another solution for this equation is 3, 3, 3, right? 3 times third is 1. And you get a triangle with all edges the same, with all angles the same. And the last solution is a 2, 3, 6, which is somewhere between these two triangles. So now that you know all of the shapes of triangles that can tile the plane, let's see them in action. Okay, so we start with the 2, 4, 4 triangle, and we see here a very small portion of the full tiling with this triangle. So this is a 2, 4, 4 triangle, and all of the rest are its reflections. Now if we want to see other parts of the tilings, we can move around, add a little bit of dynamics, and see them moving here. Okay, but let's see another interesting thing. At this point, these are only white and black triangles, and if you want, we can add a little texture to it. So let's add it. Okay, so I have some picture in the background, and for a single triangle, I take the image from this picture. And in the rest of the triangles, I just take the reflection. So this is a reflection of this image, and this image is a reflection of this image, and so forth. And again, I can take a little bit of dynamics and move around the tiling itself. But here I can even do something much more interesting. So let's stop the moving. And instead move the entire tiling, I will just move the place from which I take the image. So we can see it like this. Right, so all of the tiling stays in place, and I only move the image itself. And now I can combine the two dynamics and move the full tiling and the texture. And let's remove the black triangles, and we'll get this nice animation. Okay, so this is the 2, 4, 4 triangles. Let's look at the 3, 3, 3. So this is the tiling with the 3, 3, 3 triangles. So for example, let's add back the black triangles. So you see, these are all 3, 3, 3 triangles. And I can remove them again and see the texture. And let's look at the 2, 3, 6. So this is the 2, 3, 6. And again, I can add back the black and white triangles. So let's just see one thing. If you look at this pattern, where do you see the 2, 3, 6? Well, this is the 2. You see exactly 2 black triangles and 2 white triangles. Right? Because what does the 2 mean? 2 means that the angle is pi over 2. Or you can think about it as 2 pi over 4. Meaning that we have the same angle 4 times. So the black 2 and the white 2. So these are 2 black, 2 white. This is 3 black, 3 white. And these are 6 black and 6 white. So you can see by the number of black triangles or the number of white triangles around a vertex, you will know exactly what is the angle. Okay, so this is the 2, 3, 6. Okay, so up until now we assume that the sum of the angles is exactly pi, right? Because this is what happens in a triangle. But what happens if we don't assume it? For example, what happens if the sum of angles is larger than 1? One such example is if all the numbers are 2, so all the angles are pi over 2, or if you want 90 degrees. But we know that there are no triangles where all the angles are 90 degrees. But is there another triangle? Is there another geometry where this is true? Well, apparently there is. So let's see it in action. So if I move from 2, 3, 6, let's go first for the triangles. I move from the 2, 3, 6 to 2, 2, 2. So I get something really interesting. Instead of the standard plane, I get a sphere. So let's stop. And you can see that this is a triangle, whatever a triangle means inside a sphere. And all of the angles are pi over 2. All of the angles are 90 degrees. So in a sense, if we break our equation that the sum of angles must be 1, and instead say that the sum of angles is larger than 1, then there is a solution for it. We just need to change our geometry. So instead of the standard Euclidean geometry, we need to talk about the spherical geometry. So what does it mean to be a triangle in the spherical geometry? Well, instead of lines like the Euclidean space, we take these sort of lines, these large cycles. And indeed, there are these large cycles, which are the analog for the straight lines. And in what sense they are analog? If you take 2 points on the sphere and you want to ask what is the shortest route to get from one point to another, this route is always part of a large cycle. So in our case, this is a large cycle, this is a large cycle, and this is a large cycle. If you want a circle is a large circle if it has the same radius as a sphere. And here also I can add some texture. Let's add it. And I can move the sphere around, and I can move the texture around and see all sorts of interesting stuff. And I can see it in 2, 2, 2, I can see it in 2, 3, 2 or 2, 3, 5. All of them, the sum is larger than 1. Right, I can add back the triangles. Okay, so this is what happens if we take the sum of the angles larger than larger than pi. What happens if the sum is smaller than pi? So 2, 3, 5 is the sphere, 2, 3, 6 is the standard Euclidean space. What happens when I go to 2, 3, 7? So in 2, 3, 7 we see this interesting phenomenon. So this is called the, instead of the spherical geometry, this is called the hyperbolic geometry. So this is a new geometry for the space in which this condition, the sum of the angles, is smaller than pi. The hyperbolic geometry is much more complicated and usually much more interesting than the spherical geometry or the Euclidean geometry. And I will not go into details too much in this geometry, but I do want to say what are the straight lines, right? What are the shortest route between 2 points? So here we have two options. Either you are a vertical line or you are a half circle. So we can see these two examples here. This is a vertical line. This is the shortest route between 2 points. And if you don't look on the vertical line, we look on the half circle. So for example, this is a half circle. Half circle which starts and ends at the x-axis. So this is in general, the starting point for hyperbolic geometry. So again, we can add the texture and we can move it around, and you can see that the movement here is much more interesting. And our original example that we started in the beginning of this video was of this hyperbolic geometry. And again, we can move the texture around like this, which gives you a very, very nice and interesting animation. So one of the things that I want to talk about hyperbolic geometry. So let's stop the movement and let's go back to the triangles. In general, for the hyperbolic geometry, we need that the sum of angles is smaller than 1. So 1 over L plus 1 over M plus 1 over N is smaller than 1. So if we take L, M, and N very, very large, this is still true. And in general, we can go all the way up to infinity. And in this program, I can go to infinity, and infinity here is 1. So for example, I can take all the angles are 1 over infinity, sorry, pi over infinity. Basically, the angles are all 0. And here you have a triangle where all the angles are 0. This is a 0 angle, this is a 0 angle, and this is a 0 angle. So this is a very nice and interesting phenomena that we have in the hyperbolic geometry. We can have triangles with 0 angles. And again, I can add back the texture, I can move it around and move the tiling around and get all sort of nice animation. Okay, I think that this is enough for today. I will add links to this program in the description of this video, and we will meet next time.